Hello. This week I am taking a small detour into what most researchers would call neural network territory. However, I disagree, because we will be taking a look at the WISARD pattern recognizer. While this is usually described in the academic literature as a form of neural network, it is really just an addressable memory. Certainly, if it is a neural network, then it's the least neural networky of them all, if there is such a word. WISARD, spelled with an S, is so named after the three computer scientists who developed it. The acronym stands for Wilkie Stoneham Alexander's Recognition Device, after Bruce Wilkie, John Stoneham, and Igor Alexander. However, it is Igor Alexander who is most closely associated with it. In fact, if you want to look up WISARD on the interweb, you'll probably have to do it going via Alexander's name, as the bloody search engines keep correcting it, in inverted commas, to WISARD with the letter Z. This is an addressable memory. It's the sort of thing that you would find in an electronics course if you have been taught how to build a computer. Indeed, these things are so common in computer science that integrated circuits are produced which specifically implement the things. Essentially, the memory is a series of slots, each of which can store one binary bit of information, a 1 or a 0. It's like a series of pigeonholes. We need a way of accessing any particular slot, either to read what it contains or to write in a new value, achieved using a number of input signals. The input signals are also binary bits, 1 or 0, and read together as a binary number, they specify a particular slot in the memory. These lines form the address of that particular slot. This is exactly how a computer memory chip works. You might see the sort of thing on the right-hand side of the screen as part of a circuit diagram. The chip has a number of address lines, a read-write control, which specifies whether to read a value from memory or write a value into memory, and a line for data, which is the single bit to place into the specified slot or where the value read from memory is placed. And here we see an image of a letter consisting of 64 binary digits, black or white, arranged in a grid 8 pixels by 8. I've taken an addressable memory with 4 address lines and connected each of those lines to 4 pixels placed at random in that image. Taking a black pixel to be a binary digit 1 and a white pixel to be a binary digit 0, we can turn those 4 pixels into a 4-digit address that accesses a single slot, a single value in that memory. In the case of the letter A image, the address accessed is 0101. The addressable memory has 16 memory slots, which is 2 to the power of 4, and they are all initially set to 0. Now we have specified one in particular, and we put a digit 1 in that slot. Now I have added another 2 addressable memories and connected each of them to 4 pixels in the image at random, making sure that no pixel contributes to more than one addressable memory. The whole thing is starting to look like an explosion in a knitting factory, so you might like to pause the video and trace each of those coloured lines from a black or white pixel to a digit 1 or 0 on one of those memories. In each case, the memories all contained nothing but zeros, but the memories are set to digit 1 for the slots that correspond to the pattern of pixels in that letter A. You can probably see where I'm going with all this, can't you? There are 64 pixels in this image, which means we could hook these pixels up to address lines of 16 4 address line memories, 16 being 64 divided by 4, without any pixel being connected to more than one memory. No, I'm not showing all 16 of these memories on the screen, as it will be impossibly messy. If we put up an image of an A and specified a digit 1 for all of the memory slots accessed, then that same letter A would always cause all 16 of those memories to produce a digit 1. The output would be unanimous. In the literature, those addressable memories are called discriminators, and that's what I shall call them from here on. We present the pattern for A that we use to set up the discriminators, and surprise, surprise, all 16 discriminators produce a 1 output. Now we present a different pattern for letter B. There may well be some discriminators that still produce a 1 output, as the two patterns do have a large number of pixels in common, especially zeros. However, the score for letter B will inevitably be lower than for A, as some of the discriminators will have different addresses presented to them, corresponding to zeros as well. So, Those 16 discriminators are capable of recognizing the letter A on which it was trained, in effect. Of course, if you presented a slightly different version of A, that would lower the score, as shown. But that's not a problem. After all, each of those discriminators has 16 memory slots, and so far we have used precisely one of them in each discriminator. Present another version of A, and get the discriminators to learn that by writing a 1 into the memory addresses that they find on their 4-bit address lines. Now the discriminators will produce a perfect score of 16 ones for both the original A and the new version of A, and a smaller score for other patterns. Of course, we might want something that is a little more sophisticated than just asking, is this a letter A or not? We might want to distinguish A's from B's from any other pattern. In that case, we will need another set of 16 discriminators, all flushed out completely with zeros, and then presented with different versions of B, for instance. The appropriate slots in this new set of discriminators are set to 1. Now we have 2 sets of discriminators, each capable of scoring, in inverted commas, a pattern placed in that 8x8 grid, with scores ranging from 0, meaning I don't recognize this at all, to 16, meaning this is a pattern I have been trained on. With good training, one set of discriminators will produce a high score for any A and a low one for any B. The other set will produce a high score for any B and a low one for any A. For any other pattern, such as an X, both sets will produce low scores. And that's essentially how the WISARD architecture works in recognizing patterns. You have a series of these discriminators for each pattern that you want the system to recognize. Each discriminator has its address lines connected to pixels in the image randomly, so that there are no overlaps and each pixel is accounted for. Then you present an example of one of the patterns to those lines, and ensure that the slots selected in the discriminators corresponding to that pattern produce a 1. Repeat for the other examples of that pattern, then repeat the whole procedure for the other patterns, training the appropriate sets of discriminators in the same way. Finally, to test the whole system, present an example of one of the patterns that the discriminators haven't seen yet. Whichever set of discriminators produces the highest number of 1s gives the pattern that the system thinks has been presented. Personally, I can't see why people think that WISARD is some sort of neural network. I suppose you could see something of a resemblance between a brain cell and a discriminator, insofar as they both have several inputs and they both produce an output. But normal neural networks have complex arrangements of these things, whereas the discriminators connect the input on the grid to the output directly. They don't even talk to each other, but simply operate independently. Anyway, given that others classify WISARD as a neural network, I suppose I should list its advantages and disadvantages compared to other neural networks, such as a multi-layer perceptron. Yes, I know I haven't covered things like that yet, but I will get round to it. Here goes. Well, you've already seen the first advantage. WISARD can be trained on any given pattern in one step. For instance, if you have an example of letter A and you want WISARD to learn it, you just slap it on the input grid, tell the discriminator for letter A, learn that, then it's done, and you need never present that pattern ever again. With a multi-layer perceptron, training typically lasts overnight, or even all week. You present the training patterns for all the different categories, letters of the alphabet or whatever, in turn, and repeat the same list over and over again, many times until all connections have adapted. It takes forever. With multi-layer perceptrons, the final state of the network is always some sort of compromise, able to recognize each of the test patterns well enough to classify it correctly. The trouble is that the numbers in the network needed to encode the different patterns are all overlaid on top of each other, connecting the same set of units. Changing any one of these numbers might improve the neural network's ability to recognize the letter A, for instance, but at the slight expense of being able to recognize the letter B. Now, a carefully designed multi-layer perceptron gets round these problems by having enough connections between internal units to store all the information and still manage to classify the input patterns well enough to be useful. But it can be problematic, and you might even see your network improve its ability to classify one pattern, only to lose the ability to classify another. Not a problem for WISARD. The discriminators for classifying A's and B's are kept totally separate and never interact with each other. This means that however well you train it to recognize one letter, its ability to classify the other remains unaltered and independent. It's the same with adding new classes of patterns. Suppose you want your wizard to recognize the letter C as well. Just add another set of 16 discriminators and train them on various versions of letter C. The discriminator for A and B will simply sit there, unaffected in any way. The final advantage isn't that important to computer scientists simply trying to implement these systems in software. It's that WISARD is fairly easy to implement in hardware. Indeed, the whole thing was inspired by standard computer memory chips in the first place, so you can pretty much build one with nothing but standard components off the shelf. Of course, there is one major disadvantage. It's less noticeable for our small example of an 8x8 image, but WISARD architectures can require some hefty amounts of storage. Let's do a back-of-the-envelope calculation. To recognize our letter A on an 8x8 grid, we need 16 discriminators, each of which has 4 address lines. 16 times 4 is 64, which is 8 times 8, so yep, that makes sense. The 4 address lines enable the discriminator to store 2 to the power of 4, i.e. 16, bits of information. So 16 of them will store 16 times 16, i.e. 256 bits of information. That doesn't seem much, but that's just to recognize the letter A. A set of discriminators for every letter of the alphabet would require 256 times 26, equals more than 6.5 kilobytes. WISARD architectures that do useful work in the real world typically have to deal with images that are anything from 250 to 1,000 pixels in each dimension. A similar calculation for even a small image of, say, 256 pixels in width and height shows that it would require 262 kilobytes of data just to be able to classify one pattern. Now you can see why we specified that there had to be no overlaps in connecting the address lines of the discriminators to the image grid. We needed to have every pixel in the image accounted for, but didn't want to have any more discriminators than we really needed. Of course, if things like available memory and runtime are no object, then you could build in some redundancy to your system. Instead of having 16 discriminators with 4 address lines each, you could have 30 with 6 address lines each. Of course, you'd swiftly run out of pixels in the image to connect those lines to, so many pixels would end up feeding addresses to more than one discriminator. However, this setup might well be more likely to classify different variations of the trained patterns correctly. Again, it will be necessary to make sure that every pixel in the image was connected to at least one address line, and no 2 discriminators should be connected to exactly the same combination of pixels, simply to avoid duplication. In general, adding redundancy to the system tends to make it a more robust pattern classifier. One question that's asked about WISARD is, why are the connections assigned at random? Wouldn't it be easier simply to assign connections along rows until you ran out of pixels? Well, that would indeed be easier to program, but it introduces an element of brittleness into the recognition. Consider the situation where 2 discriminators are assigned addresses in order along the top row. These 2, like all the others of their set, have been trained to recognize an uppercase letter T as shown. But now the T is replaced by a slightly shorter variation. Will the discriminators still recognize it? Well, those 2 won't. Suddenly each of them goes from an input address 1111 to an address 0000. The WISARD system is more likely to classify that pattern as a letter I than a T. Had the connections been assigned randomly, this would be less likely to happen. Of course, a practical WISARD architecture will be trained on several examples of uppercase T, and would probably not have failed in this case. But it is generally found that assigning connections at random avoids brittleness like this in pattern recognition. Another question that is asked is, how many address lines should each discriminator have? In this case, I chose 16 discriminators, each with 4 address lines, but I could just as easily have chosen 8 of them with 8 lines, or even 2 with 32 address lines each. WISARD works at its best when it has a sizable number of discriminators to classify each pattern. If each class of pattern has only 2 discriminators, then the score for that class can be only one of 3 different values, 0, 1, or 2. It becomes hard to distinguish between different classes when faced with a series of 1s, or even a few 2s and 1s. Having a considerable number of discriminators allows different but similar classes, such as uppercase T and I, to be better distinguished. On the other hand, having too many discriminators per class doesn't allow for general representation of patterns to be developed. In the extreme case, where we had 64 discriminators to classify each pattern, then each of them will be a single element connected to a single pixel. Effectively, each discriminator would simply duplicate the pixel to which it was attached, producing 1 when the pixel was a 1 and 0 when it was 0, or vice versa. In this case, instead of general pattern recognition, our WISARD system simply becomes a series of lookup tables, where each class of pattern is represented by a number of examples. When a test pattern comes in, we simply look in the table to see if it matches any of the known examples. No match, no recognition. That not only doesn't work particularly well, but it hardly counts as artificial intelligence either. In general, you have to judge how many discriminators you should have, with how many address lines each, using experience, and try different combinations until you get the best, most robust recognition. Of course, there is nothing to stop you having a large number of discriminators with a large number of address lines, providing you are willing to dedicate a great deal of memory and processing power to the whole thing. One extension of the WISARD architecture is to make it recurrent. This happens when the output connections are fed back into the inputs a little while later. In general, there is some sort of ticking clock in the background, and the outputs that the system produces on one tick of the clock become the new inputs on the next tick. In this case, there are 64 different discriminators, each producing an answer of 1 or 0, and these values are used to replace the input pattern and become the new grid of 8 by 8 pixels on the next tick of the clock. Of course, you should note what I said above about having excess discriminators, but it doesn't apply in this case, as each discriminator is still connected to 4 address lines. This means, of course, that each pixel has to feed not 1, but 4 different discriminators. Training is equally easy for the recurrent WISARD. You present a pattern on the input and adjust the contents of the discriminators so that exactly the same pattern is produced on the output. If this pattern were then to be represented as the new input, nothing would change, as it already has been trained to produce that exact same pattern again. Another different pattern will be presented to those same discriminators, and the system will be trained to produce that very same pattern again. The idea in this case is not simply to classify a pattern as one of a few types, but to complete a pattern and tidy it up. For instance, if the system had been trained on a single example of a letter A and a single example of a letter B, then you could present a corrupted version of one of the letters on the input grid. The system would then run by itself, using its own output as its next input, and the output would change gradually until it became one of the standard patterns which it was trained to recognize. At that point, the system has entered a stable state, as no further change will be possible. This way, an incomplete or dirtied version of any of the standard patterns will be cleaned up and repaired to become one of the trained patterns themselves. Of course, the system hasn't actually recognized it as such, but it is then a simple matter to add a bit of code that will tell you which pattern that was. So, there you are. There's a great deal to explain about the WISARD architecture, and as you might be able to tell, I'm quite fond of it. In fact, I might even indulge in 2 JavaScript projects for WISARD rather than just one, so that I can give you a bit more information about that recurrent version, as well as the straightforward simple classifier. Everything should then become clear. Watch this space, folks. Thank you.